Alright, in the previous videos we showed you how to transfer a polar function back and forth from a rectangular coordinate to a polar coordinate, and we may how to check the curve, how does it behave accordingly to each one another, and we showed that it matches all the points, and all it is that with a rectangular coordinate we have according to certain horizontal values, we have another vertical values. Here is we have a point, and how far away is it from the origin and how much is it being elevated up. If it's a positive r, or positive distance away, it will be going along the elevation. Let's say you have pi over 4, 45 degrees going that way. The positive distance away from the origin will be along that direction. But if it's negative, it will be going on this way, the negative way. Alright, so how do we continue from that? Or one may say, how do we calculate the length of a polar curve? Before, in the previous videos, we showed you how to calculate or derive the equation calculating the length of a parametrized curve. And with this one, it may look similar to a parametrized curve, because if you look at the x coordinate, you have you have x, right? If x is the coordinate, you have x equal to sine, cosine, theta. R times cosine theta, and y equals to r sine theta. Alright, so you may look at this as x is just a function of theta, in a sense, right? You can think of this just x theta, and this will be y theta. Where in the parametrized curve, we say that x could be x is xt of some function ft, and yt be some function of gt, maybe. But the thing is, parametrized t doesn't limit itself to be time. It could be anything. In fact, it could be that theta, right? And here we have it. R is a function of the theta. Therefore, r becomes a function of theta. A function times a function that's itself is a function. So we have x is a function of theta, and y is a function of theta. Alright, so how do we go ahead and derive the length of a polar curve? Well, in the previous sessions, we showed that to calculate the length of a parametrized curve, we know that the length of that curve would be t going from some, let's say, time, from time A to time B, and it's the square root, and we calculate to be the dr over dt. dr over dt and dr over dt, we show that it's just the scalar of the r prime vector, right? R prime vector, and that's just that scalar. We take this magnitude of this, so it becomes dx over dt squared plus dy over dt squared, and dt, because we know that dr over dt times dt, right? So that's why we have a dt out there. Alright, so this is the form for the parametrized curve. But how do we relate from this form going to that form? It's not quite the same, but it will be following the same principle. Alright, so we know that dx dt, so we know that we have to take the derivative of this. So we know that, alright, so we may say, so we keep that in mind, keep that equation in mind. So this curve, we may imagine this, how to calculate the length of this, maybe there's a certain, so we have x equal to r cosine theta. We know that we can take a derivative of this because we think about dx over dt. So instead of t, we put in theta, dx over theta. So what dx d theta equal to? Well, we know this is a function times a function, so we know that we're going to use the product rule where we do the differentiating. Alright, so we do with r first, would be dr d theta times cosine, right, plus minus sine, maybe we should write minus sine theta times r, right? What about dy d theta? dy d theta r sine theta do the product rule, the dr d theta sine theta plus r cosine theta. And we know that we got to square each term of this, right? Alright, so when we square this, we can, what do we have? So when we square that, we will have dx over d theta squared. Not the second derivative, but square of that. So just times it by itself. So that will be r prime squared, r prime cosine together square, right, minus r sine squared plus, or minus, right, minus 2r prime r sine theta cosine theta, right? Alright, for dy d theta, square of that, you have r prime sine theta plus 2 r prime r sine cosine plus r cos squared. Alright, we see when we plus these two entities together, we know that these minus r prime r sine theta cosine theta and this is a minus and plus, this cancel, right? So this cancel. Alright. I'm sorry, this is a plus. Alright, so plus this is r squared. You might put r squared outside, right? Sine squared plus cosine squared, that's 1, so it become r squared. So we will say dx over d theta squared plus dy over d theta squared. That is r squared. This plus this, well, same way, sine squared plus cosine squared, that's 1, becomes r prime squared. Alright. So now that's pretty much it. That's pretty much how we will do it. And remember there's the square root here. Therefore we have a square root. Alright, so let's write everything again. We will have length of a polar function of a polar curve will be, because we calculate in terms of theta, so we may go from some angle alpha to some angle beta, right? And we know that is the square root of dx d theta squared plus dy d theta squared. And we have dx d theta squared plus dy d theta squared. We will have to figure it out, which is r prime. Of course, it's theta, right? But for the sake of simplicity, we may put it r prime squared plus r squared d theta. Alright, so that is your length of, that is the equation calculating the length of a polar curve. Theta goes from some angle alpha to some angle beta. Square root r prime of theta. So if you have r go f theta, take the derivative, so square it up, plus r squared, which is itself, the function f theta, and then plus it together, and then take the square root, and d theta. Alright. So, thank you very much.